All right. I have to go back to 1173. I have a problem with the video there. 1173. All right. Sample of carbon monoxide is prepared and collected over water. 22 degrees Celsius. Total pressure was 754. 754, 22 degrees Celsius. That's torr. But this is due to the carbon monoxide and the water, right? Because we know that when you collect over water, some of the water is in vapor phase. So, we have to find out how much torr is due to the water and subtract it so that we can find out how much pressure is actually due to the carbon monoxide. All right? And then we need to determine how much volume that would be. Like it says, first of all, calculate the partial pressure, and then find out what the volume would be under 1 atmosphere and 25 degrees Celsius. So at 1 atmosphere, or 760 torr, right? And 25 plus 298 Kelvin, what would be the volume? So this is pressure 2, volume 2, temperature 2, and that's equal to, all right, we can use that relationship there. We have pressure 1, V1, T1 equal P2, V2, T2, correct? So, we're going to find out what the initial pressure was. It's going to be whatever this pressure was here. And the initial volume is 268, is that right? And the initial temperature was 295, 22 plus 273. All right, so where do we get this? Well, it's not on page 500 because 22, but at the bottom of the one on page 500, the table on page 500, it says go back to the appendix C. Back in the back of appendix C, it indicates that the partial pressure is 19.8. So 754 minus 19.8, that equals 734.2. Multiply that by 268, divide that by 295, divide by 760, times by 298, and that gives me 261.5 milliliters. All right, so here's what's our partial pressure? Our partial pressure was 734.2, and this is the volume that we expect. 1173, 734, and 262. All right, 735. Or 1175. 1175. What volume of wet methane would you have to collect at 20 degrees Celsius and 742 torr to be sure that you had the sample containing 244 milliliters of dry methane, also at 742 torr? So at 742 torr at 20 degrees Celsius. Well, that's on the page on 500, right? On page 500, 20 degrees is 17.54. So 17.54, that pressure is due to the oxygen. So this is due to the carbon dioxide and the oxygen, or the water, sorry. And this is due just to the water, right? And, oh no, this is methane we're collecting, CH4. So then, if we subtract these two, we'll find out what partial pressure of the methane is. 742 minus 17.54. And it's 724.46. So we knew that the volume, we want 244 milliliters of dry methane. We want 244 milliliters, right? Well, if I got 244 milliliters of the gas at 742 torr, then I know that 17.54 of it would be from the water. So I would have to I want to get that much methane. That's how much gas I would get. Some of it would be water. So what I have to do is find out how much would actually be methane. I can do that by looking at this ratio, taking 724.46, that's how much was the methane, pressure due to the methane, divided by 742, the total pressure, and that gives me a fraction. And I can multiply that fraction times 244, and that'll tell me how many milliliters of methane I actually get, and that's 238. So I had to add, I lose 4 milliliters due to the water. So if I want to get 244, not 4, but 6, right? 238 to 244. So if I want to get 244 of methane, I need to add 6 more milliliters. So that's going to be about 250 milliliters of methane, maybe slightly more. So 1175, if I give 250 milliliters of gas under these conditions, I'll get 244 milliliters of methane. That was 1175. Okay, 1177. Under the conditions in which the density of carbon dioxide is 1.96 and that of nitrogen is 1.25, which gas will effuse more rapidly? Well, we know that the lighter and the less dense will effuse more rapidly. So that is nitrogen gas. Nitrogen gas will effuse more rapidly. And we know, based on page 520, that there's a relationship between the diffusion rate of A over the diffusion rate of B, and either the density of B over density of A, square root of that, or the molar mass of A, molar mass of B over the molar mass of A. Okay? So in this case, we want the density, well, we want to find the ratio here of nitrogen over carbon monoxide, because that's what it says there. So we want nitrogen to be on the bottom, so the nitrogen over carbon monoxide here. So nitrogen is 1.25 and 1.96, so the square root of 1.96 over 1.25 should be the diffusion rate. So 1.96 over 1.25, and then I take the square root of that value, and I'm getting the 1.25 will be the rate of A over B. 1177. Okay, 1.25. All right. Uranium hexafluoride is a white. Okay, 1179. Uranium hexafluoride is a white solid that readily passes directly into the vapor state. Its vapor pressure at 20 degrees Celsius is 122 torr. A trace of uranium in this compound is about about 0.7% is uranium-235, which can be used in a nuclear power plant. The rest of the uranium is essentially uranium-238, which its presence interferes with its applications for uranium-235. Gas effusion of uranium fluoride can be used to separate the fluoride made from uranium-235 from the fluoride made from uranium-238. So, which hexafluoride fuses more rapidly? And by how much? You can check your answer by reading that book there. So which is going to diffuse more rapidly? Well, the one with the smaller mass, which is the UF6. And what will be, how much faster will it, by how much? Which one diffuses more rapidly and by how much? Okay? So if we know the, we want to get the rate of effusion of the, again, rate A over rate B over rate A, molar mass of A over molar mass of B, square root of that, right? So we'll get the faster effusing one here over the slower one, and that'll tell us how much faster the faster one goes. So we'll have the lower mass one up here, which is UF. Oh, they're both UF6, right? So we just need to identify the molar mass of UF6. Uranium-235 and 238. So 235 for the uranium-235 fluoride. Let's see, 6 fluorines is how much? 19 times 6. So the mass of the uranium-235, which would be the faster one, is 349. Oops. So this is the UF6-235, and that's 349. Excuse me. Now UF6 with the 238. So 238 plus 19 times 6. That's 352. And so this will be the 238's rate, UF6. So how much faster? Well, it's going to be the answer to this right here. 352 divided by 349. 352 divided by 349. So I'm getting 1.0042. Let's see if that's right. 1.00428, 1.0043. So that's how much faster uranium-235 is going to diffuse. And that's how they make nuclear bombs, right?